On December 25, 2021, a telescope unlike anything humanity had ever built left Earth's orbit, carrying with it the capacity to see what should be impossible. The James Webb Space Telescope wasn't designed to confirm what we already knew. It was built to shatter our understanding of cosmic history, and within months of operation, that's exactly what it started doing. What astronomers found wasn't just surprising. It was fundamentally wrong according to every model we'd spent decades perfecting. Galaxies that shouldn't exist. Structures that couldn't have formed. Chemical signatures that violated the timeline of stellar evolution itself. The deeper Webb looked into the ancient universe, the more it revealed a cosmos that had no business being so advanced, so organized, so impossibly mature at such a young age. This isn't a story about incremental scientific progress. This is about watching the foundations of cosmology crack open in real time. Webb orbits the Sun at a point called L2, positioned 1.5 million kilometers from Earth. That's not an arbitrary location. L2 represents a gravitational balance between Earth and the Sun, a sweet spot where the telescope can maintain position with minimal fuel while keeping its instruments perpetually shielded from solar radiation. The positioning matters because Webb doesn't observe invisible light like Hubble. It sees in infrared, detecting heat signatures and wavelengths that pass straight through cosmic dust like it isn't even there. That 5-layer sun shield isn't just protection. It's the difference between detecting a galaxy 13.5 billion light-years away or seeing nothing but noise. But here's what makes this telescope truly revolutionary. When Webb looks at distant galaxies, it isn't just seeing farther than previous instruments. It's seeing through barriers that have hidden entire populations of cosmic objects from human observation since we first pointed telescopes at the sky. Dust clouds that blocked Hubble's view become transparent. Star-forming regions shrouded in gas suddenly reveal their internal architecture. And galaxies that appeared as faint smudges in earlier surveys transform into detailed structures with visible spiral arms, stellar bars, and active cores. The first major discovery hit the astronomical community like a shockwave. Webb detected a galaxy designated JWST 14-0, existing just 280 million years after the Big Bang. Its light had traveled 13.5 billion years to reach our instruments, making it the most distant galaxy ever observed. That alone would be remarkable. What made it genuinely disturbing was what Webb found inside the galaxy. It was bright. Far brighter than theoretical models predicted any galaxy could be at that cosmic epoch. It was compact, with stellar densities that suggested rapid, efficient star formation. And most troubling of all, it was chemically enriched with heavy elements that shouldn't exist yet. Spectroscopic analysis revealed elevated nitrogen levels, which meant multiple generations of massive stars had already lived, evolved, and exploded as supernovae, seeding the interstellar medium with fusion products. The problem? That cycle takes time. Lots of time. To produce the oxygen detected in JWST 14-0, stars had to form from primordial hydrogen and helium, fuse lighter elements into heavier ones over millions of years, then violently die in supernova explosions that scattered those elements into space. New stars had to condense from that enriched material, repeating the process. This isn't a quick sequence. Yet somehow, this galaxy accomplished multiple stellar generations in what should have been cosmic infancy. One researcher put it bluntly, it's genuinely mind-boggling. JWST 14-0 isn't alone. Webb has identified hundreds of galaxies in the early universe that are 100 times brighter than theoretical studies predicted before launch. Not 10 times. Not 50 times. 100 times. That's not a minor calibration error in our models. That's a fundamental misunderstanding of how galaxies assemble in the first billion years after the Big Bang. The gap between theory and observation has grown so wide that some astronomers openly question whether our entire framework for early galaxy formation needs rebuilding from the ground up. Consider what this means practically. Before Webb, the standard cosmological model predicted that large, complex galaxies would take several billion years to form through gradual mergers of smaller protogalaxies. The early universe was supposed to be populated by dim, irregular clumps of stars slowly coalescing into recognizable structures. Instead, Webb found mature spiral galaxies with well-defined arms, central bulges, and organized rotation patterns existing when the universe was barely 10% of its current age. The galaxy nicknamed Big Will exemplifies this impossibility. Observed as it appeared roughly 2 billion years after the Big Bang, Big Will stretches more than 100,000 light-years across. That's larger than any confirmed galaxy disk from this cosmic epoch. It's 5 times more massive than the Milky Way and twice as wide. The kicker: it displays perfect spiral structure, the kind of ordered morphology that supposedly requires billions of years of gravitational settling and angular momentum distribution. Yet there it sits in Webb's infrared images, impossibly organized, impossibly large, impossibly early. Then there's JWST, a candidate for the most distant spiral galaxy ever detected. Dating to approximately 1 billion years after the Big Bang, it resembles our Milky Way with disturbing precision. The name comes from a Himalayan river, chosen by the Indian astronomers who discovered it. JWST shouldn't just be surprising. It should be impossible. Current theories explicitly predict that galaxies this structured don't appear until much later in cosmic history, after repeated merger events have smoothed out irregularities and established stable rotation. Finding one this early is like discovering a modern skyscraper in an archaeological dig that should only contain mud huts. What's causing this impossible maturity? One hypothesis suggests stars formed more efficiently in the early universe than they do today. Perhaps the initial density of gas clouds or the absence of heavy elements that impede star formation allowed primordial galaxies to convert hydrogen into stars at rates we can't replicate in modern observations. Maybe in the early universe, galaxies were simply better at turning gas into stars, achieving in hundreds of millions of years what now takes billions. But that explanation creates its own problems. If star formation was more efficient, we need to explain why. What physical mechanism would cause such a dramatic difference? And if that mechanism existed, why did it stop? The early universe wasn't fundamentally different in its physical laws. The same gravity, the same nuclear forces, the same electromagnetic interactions governed cosmic evolution then as now. Invoking a mysterious efficiency boost feels less like solving the puzzle and more like naming our ignorance. Another possibility involves dark matter. Shortly after the Big Bang, the universe wasn't perfectly uniform. Quantum fluctuations in the primordial density field created slight variations, regions where matter was marginally more concentrated than elsewhere. Those density peaks acted as gravitational seeds, attracting surrounding material and growing into the cosmic web of filaments and voids we observe today. For ultramassive galaxies to form as quickly as Webb observes them, perhaps more of these high-density regions developed immediately after the Big Bang than our standard cosmological model predicts. This explanation preserves existing physics but requires adjusting the statistical distribution of primordial density fluctuations. Teams at Johns Hopkins University have explored whether such modifications are necessary or even plausible. Their preliminary conclusion: the standard cosmological model might not need revision after all, but our understanding of how galaxies formed and evolved within that framework almost certainly does. The universe's expansion rate, its matter and energy content, the behavior of dark matter and dark energy may all remain unchanged. What needs updating is the messy, complicated process by which gas collapses into stars, stars organize into galaxies, and galaxies grow into the structures we observe. Yet even as astronomers grapple with these massive, mature galaxies, Webb revealed something stranger hiding in the cosmic shadows. Objects that look completely different depending on which wavelength of light you use to observe them. Galaxies that appear ordinary in optical surveys but transform into monsters when viewed in infrared. Hidden populations of extreme objects that previous telescopes missed entirely because they were looking at the wrong wavelengths, seeing only half the picture, blind to what was really there. The discovery of these hidden structures didn't just add new data points to existing catalogs. It suggested that our census of the early universe might be fundamentally incomplete, that we've been systematically overlooking entire categories of galaxies and phenomena because we weren't equipped to detect them. And if that's true, then every conclusion we've drawn about cosmic history based on incomplete observations needs re-examination. Every timeline, every formation model, every statistical analysis built on data that missed the most extreme objects. What Webb found when it looked at these hidden galaxies would force astronomers to confront an uncomfortable question: what else have we been missing? The answer came from an unlikely source. A galaxy nicknamed Virgil. When astronomers first observed Virgil using optical wavelengths, the kinds of light our eyes can see, it looked unremarkable. Just another star-forming galaxy from the early universe, going about its business of creating new suns from clouds of hydrogen and helium. Nothing unusual. Nothing worth a second glance. One more data point in the growing catalog of young galaxies that Webb was steadily accumulating. But when the same team pointed Webb's mid-infrared instrument at Virgil, everything changed. The mild-mannered galaxy transformed into something else entirely. A monster lurking beneath an ordinary disguise. At the galaxy's core blazed a supermassive black hole, actively feeding, pulling in surrounding material and releasing tremendous energy. This wasn't a small black hole. This was a beast containing millions of solar masses, gorging itself on gas and dust, shining brilliantly in infrared wavelengths while remaining nearly invisible in optical light. The transformation was so dramatic that astronomers started calling Virgil a Jekyll and Hyde galaxy. Look at it one way, you see a normal galaxy. Look at it another way, you see an extreme object that shouldn't exist so early in cosmic history. The discrepancy wasn't subtle. This was a fundamental difference in what the galaxy appeared to be, depending solely on which instrument you used to observe it. Why does this matter? Because if Virgil can hide in plain sight, how many others are doing the same thing? Dust is the key. Thick clouds of cosmic dust surrounding the black hole absorb optical and ultraviolet light completely, blocking those wavelengths from escaping into space. But infrared light, with its longer wavelengths, passes through dust relatively easily. It's the difference between trying to see through fog with your eyes versus using thermal imaging. Different wavelengths reveal different realities. Webb's infrared instruments aren't just seeing farther than Hubble. They're seeing different objects entirely, galaxies and phenomena that optical telescopes miss because they're looking at the wrong part of the electromagnetic spectrum. This realization sent a shock through the astronomical community. If a significant population of dust-obscured black holes exists in the early universe, every statistical analysis based on optical surveys is incomplete. Every model of black hole formation built on visible light observations is potentially wrong. Not slightly off. Fundamentally incomplete. Teams immediately began re-examining archival data, looking for other Jekyll and Hyde galaxies hiding in datasets that had been considered thoroughly analyzed. They found them. Not just a few outliers, but a population. Objects that appeared ordinary in Hubble images but revealed extreme activity when Webb looked at them in infrared. The implications extend beyond just counting black holes. These hidden objects might have played crucial roles in cosmic history that we've been systematically underestimating. During the epoch of reionization, when the first stars and galaxies cleared the fog of neutral hydrogen that filled the early universe, astronomers have long debated which objects contributed most to that transformation. Big galaxies, small starburst galaxies, active supermassive black holes. If we've been missing a substantial fraction of the black hole population because their dust obscured, our calculations about their contribution to reionization are wrong. These hidden monsters might be far more important than anyone realized. But Virgil wasn't the only surprise waiting in Webb's data. When astronomers trained the telescope on early galaxies expecting to see chaotic, irregular blobs of stars, they found something that shouldn't exist. Spiral galaxies. Perfect, well-organized spiral galaxies appearing less than 2 billion years after the Big Bang. Joulon was the first one that made astronomers stop and stare. A Milky Way twin existing when the universe was barely 1 billion years old. The galaxy displayed clear spiral structure, organized arms of stars and gas sweeping around a central bulge. This wasn't supposed to happen. Standard models predicted that spiral galaxies required billions of years to form, emerging only after multiple generations of smaller galaxies merged and settled into stable rotating disks. The process demands time. Gravity needs time to organize chaos into order. Stars need time to form, live, die, and enrich the interstellar medium with heavy elements. Disks need time to spin up and develop density waves that create spiral arms. Yet there was Joulon, fully formed, impossibly early, challenging every timeline astronomers had carefully constructed. Then came Okanunda. Another grand design spiral, this one resembling the Milky Way so closely it could be our galaxy's ancient twin. Symmetric spiral arms. Bright central bulge. Star formation occurring at 20 times the Milky Way's current rate. All of this existing when the universe was just 1.5 billion years old, less than 11% of its current age. Indian astronomers who discovered it named the galaxy after a Himalayan river, perhaps because its spiral arms flow with the same graceful inevitability as water finding its path through mountains. These weren't the only spiral galaxies Webb found in the early universe. As teams examined more data, more spirals appeared. Cosmos 74706, sporting a prominent bar through its center similar to the Milky Way's own bar, dates back 11.5 billion years. J0107a, a monster galaxy with mass 10 times greater than our home galaxy and star formation 300 times more intense, displays a barred spiral structure so perfect it looks more like a modern galaxy than an ancient one. The pattern became clear. Spiral galaxies weren't rare anomalies in the early universe. They were common. How does a galaxy develop organized structure so quickly? The question doesn't have a good answer yet. Spiral arms form when density waves propagate through a rotating disk, regions where stars and gas bunch up temporarily as they orbit the galactic center. But creating stable density waves requires a settled, rotating disk. Creating that disk requires angular momentum to be distributed properly during the galaxy's formation. Getting everything aligned correctly is complicated, messy, and according to all previous models, slow. Except it wasn't slow. These galaxies figured it out in a fraction of the time theories allowed. Perhaps mergers happen differently in the dense early universe. When galaxies are closer together, collisions occur more frequently. But most merger simulations produce irregular galaxies, not pristine spirals. You need special conditions, specific mass ratios, particular orbital geometries, for a merger to produce a spiral galaxy rather than destroying any existing structure. Finding those special conditions once or twice might be luck. Finding them repeatedly suggests something systematic we don't understand. The discoveries kept coming, each one stranger than the last. Webb observed the earliest galaxy cluster ever seen, a protocluster assembling itself just 1 billion years after the Big Bang. Galaxy clusters are the universe's largest gravitationally bound structures, containing hundreds or thousands of galaxies held together by their mutual gravity. They're cities in a cosmic landscape, dense concentrations of matter where galaxies interact constantly, merging, stripping gas from each other, triggering bursts of star formation or shutting it down entirely. Building these massive structures should take time. Dark matter halos need to grow large enough to trap multiple galaxies. Those galaxies need to fall into the halo's gravitational well, spiral inward, and settle into stable orbits. The process involves countless small steps, each requiring millions of years. Yet Webb found a protocluster already well along that path, assembling when the universe was barely old enough for such structures to exist. Even more remarkable was a merger event involving at least 5 galaxies colliding simultaneously 800 million years after the Big Bang. Not just colliding, but redistributing heavy elements beyond the galaxies themselves, seeding the surrounding intergalactic medium with oxygen, carbon, nitrogen, the products of stellar nucleosynthesis. This kind of chemical enrichment was thought to be a later phenomenon, something that happened gradually as successive generations of stars formed and died. Finding it occurring during a massive merger so early suggests that galactic interactions weren't just building structure but actively spreading the chemical ingredients for future star and planet formation across vast regions of space. These observations paint a picture of an early universe that was far more dynamic, more violent, more active than anyone expected. Galaxies weren't slowly assembling in isolation. They were crashing together, feeding supermassive black holes, organizing into spirals, forming clusters, all while the cosmos was still in its infancy. Every discovery pushed the timeline backward, compressing events that should have unfolded over billions of years into the first few hundred million. But perhaps the most unsettling revelation involved what Webb could see when it looked at nearby galaxies, objects astronomers thought they knew well. Spiral galaxies 50 to 65 million light-years away had been observed for decades. Hubble had photographed them extensively. Ground-based telescopes had studied them in detail. They were understood, catalogued, familiar. Then Webb looked at them with its infrared instruments and revealed structures that had been invisible all along. The skeletal framework of the galaxies themselves, gas filaments, dust lanes, star-forming regions hidden behind obscuring material. One astronomer described it as seeing the galaxy's skeleton for the first time, all the connective tissue and internal structure that optical light couldn't penetrate. If galaxies 50 million light-years away still held secrets, what does that say about our understanding of galaxies billions of light-years distant, objects we can only observe as faint smudges even with our most powerful instruments? How much are we missing? How many hidden populations exist that we can't detect because we're still looking at the wrong wavelengths, still blind to crucial parts of the spectrum where the most extreme phenomena reveal themselves? The thought is humbling and terrifying. Because if our census of the early universe is fundamentally incomplete, then every conclusion built on that census stands on uncertain ground. The incomplete census goes deeper than just missing galaxies. Webb revealed entire categories of objects that appear fundamentally different depending on which wavelength you observe them with. A galaxy nicknamed Virgil looked perfectly ordinary in optical light. Just another star-forming galaxy in the early universe, nothing remarkable. Then astronomers pointed Webb's mid-infrared instrument at it and a monster materialized. A supermassive black hole, heavily obscured by dust, completely invisible at optical wavelengths but blazing in the infrared. The galaxy hadn't changed. Our ability to see what was actually there had. This Jekyll and Hyde behavior raises an uncomfortable question. How many objects have we categorized based on incomplete information? How many galaxies that appear normal in Hubble images are hiding active black holes, extreme star formation, or other phenomena that only reveal themselves at wavelengths Hubble couldn't access? The discovery suggests we might be systematically missing a hidden population of dust-obscured black holes throughout cosmic history. These objects could have played crucial roles we never knew about, perhaps even contributing to reionization, the process that cleared the fog of neutral hydrogen filling the early universe. The implications stretch beyond individual objects. If our census is incomplete, then our understanding of cosmic evolution rests on a dataset full of gaps. We've been building theories based on what we could see, not necessarily what was there. It's like trying to understand a city's economy by only counting businesses visible from the street, missing everything happening in basements, back rooms, behind tinted windows. Webb's multi-wavelength capabilities, combining near-infrared and mid-infrared observations, function like removing those barriers. The telescope doesn't just see farther. It sees differently. Its instruments span wavelengths from 3 to 28 microns, detecting chemical fingerprints from molecules in gas form, signals from frozen ices, thermal emission from warm dust. Each wavelength reveals different physical processes, different components of the cosmic ecosystem. Put them together and you get a picture that's not just higher resolution but fundamentally more complete. Take the organic molecules discovered in a nearby galaxy's core. Benzene, methane, acetylene. Complex carbon compounds in one of the harshest environments imaginable, deep inside a galactic nucleus where radiation and stellar winds should destroy such fragile structures. Yet there they were, revealed by Webb's spectroscopic instruments. Not just their presence but their abundance, their temperature, their physical state. This level of chemical detail in an extragalactic environment was impossible before. Now it's routine. The discovery matters because organic molecules trace chemical evolution. They show how raw hydrogen and helium get processed into increasingly complex structures through stellar nucleosynthesis, supernova explosions, and the intricate chemistry of interstellar space. Finding them in unexpected places means we've underestimated how efficiently the universe builds complexity, how quickly simple atoms become molecules that could, in the right conditions, form the basis for something more. But the chemical revelations extend beyond organics. Remember JADE's JWST 14-0, that galaxy 280 million years after the Big Bang with unexpectedly high nitrogen levels. Nitrogen formation requires multiple stellar generations. First-generation stars, formed from pure hydrogen and helium, must live their lives, synthesize heavier elements through fusion, then explode as supernovae, releasing those elements into space. Second-generation stars form from that enriched material, fuse elements further, explode. Only then do you get significant nitrogen abundance. This cycle should take time. Hundreds of millions of years minimum. Yet there's JADE's JWST 14-0, showing advanced chemical enrichment when the universe was barely old enough for the process to have started, let alone completed multiple iterations. One astronomer called it genuinely mind-boggling. Not hyperbole. The oxygen levels alone require a generation of massive stars to form, devolve, and die before the galaxy we're observing even existed in its current form. It pushes stellar evolution back to timescales that shouldn't have been physically possible. Unless star formation in the early universe operated under different rules. Maybe the first stars formed faster than modern stars. Maybe they were more massive on average, burning through their fuel in mere millions of years instead of billions. Maybe the initial conditions, denser gas, less metal contamination, different radiation environments, created a stellar population unlike anything we see today. If so, then our understanding of stellar physics, built on observations of nearby contemporary stars, might not apply to the conditions present during cosmic dawn. The evidence keeps pointing in that direction. Galaxies too bright, too massive, too chemically evolved for their age. Over and over, Webb finds objects that shouldn't exist yet according to our models. 300 candidate galaxies brighter than predictions allowed. If even a fraction of them are confirmed as genuine early galaxies, existing ideas about galaxy formation need revision. Not minor tweaks. Fundamental reconsideration. The brightness problem connects to the mass problem. To shine that brightly, a galaxy needs either an enormous number of stars or stars that are individually much more luminous than expected. Both scenarios require rapid, efficient star formation. But forming stars requires cooling gas, and cooling mechanisms in the early universe should have been less efficient than today. Fewer heavy elements means fewer pathways for gas to radiate energy and collapse into dense clouds where stars ignite. Yet somehow these galaxies overcame that limitation and produced stellar populations capable of outshining theoretical predictions by factors of 10 or more. One possible explanation involves starbursts, brief periods where star formation proceeds at rates hundreds of times higher than normal. Modern galaxies occasionally undergo starbursts triggered by mergers or gas inflows, but they're rare, temporary events. If early galaxies experienced near-constant starburst conditions, that could explain their extreme brightness. But why would starburst activity be more common in the early universe? What about those conditions promoted such intense star formation? The answer might lie in how galaxies acquired their gas. In the current universe, gas accretion happens relatively smoothly through filaments of the cosmic web. In the early universe, with higher overall densities and more frequent galaxy interactions, gas might have flowed into galaxies in violent bursts, each one triggering a wave of star formation. These cold gas streams, falling directly into galaxies without heating to the temperatures typical of later cosmic eras, could have fueled prolonged episodes of efficient star formation. Then there's the dark matter question. Shortly after the Big Bang, quantum fluctuations created tiny density variations in the distribution of energy and matter. Regions slightly denser than average attracted more material through gravity, growing over time into the large-scale structure we see today. To form ultramassive galaxies as quickly as Webb observed them, those initial density variations would need to be stronger than the standard cosmological model predicts. More pronounced peaks in the primordial density field, more regions primed to become gravitational wells capable of assembling galaxies rapidly. Some researchers initially thought this might require modifying our cosmological model, adjusting the parameters that describe the universe's composition and evolution. But subsequent analysis suggested that wasn't necessary. The standard model could accommodate these observations if we revised our understanding of how efficiently early galaxies converted gas into stars. Maybe the conversion efficiency was higher. Maybe feedback mechanisms that normally regulate star formation, supernova-driven winds, radiation pressure from massive stars, were less effective at shutting down star formation in dense early environments. What's becoming clear is that the early universe wasn't a simpler version of today's cosmos. It was a different regime entirely, operating under conditions that no longer exist, producing outcomes that contemporary galaxy formation processes can't replicate. Understanding it requires more than extrapolating backward from present-day observations. It demands recognizing that we're looking at a fundamentally alien epoch where the rules governing structure formation, star formation, chemical evolution all function differently than they do in the mature universe we inhabit. And we're only beginning to map that alien territory. Each Webb observation reveals new features of the landscape. Jellyfish galaxies with long streams of gas stripped away by ram pressure as they move through dense cluster environments, a phenomenon that shouldn't occur until much later when galaxy clusters had time to develop substantial intracluster medium. Little red dots, Mysterious objects appearing in huge numbers around 600 million years after the Big Bang, then rapidly declining by 1.5 billion years, their nature still debated, possibly dust-shrouded black holes, possibly something else entirely. The discoveries accumulate faster than theories can adapt. Every attempt to explain one observation seems to conflict with another. The universe as revealed by Webb doesn't fit neatly into existing frameworks. It's messier, more violent, more creative than anyone predicted. Which means the next revelation, whatever Webb finds when it points at some previously unexplored patch of sky, might not just surprise us. It might force us to question assumptions we didn't even realize we were making. One of Webb's most perplexing discoveries involves structures that shouldn't exist at all. Not because they violate physics, but because the universe supposedly lacked the time to build them. Take JWST, a spiral galaxy appearing just 1 billion years after the Big Bang. It's not a small irregular blob, the kind of primitive structure you'd expect from an infant cosmos. It's a fully formed grand design spiral, displaying two symmetric arms, a bright central bulge, organized rotation. A galaxy that looks remarkably like the Milky Way, except it existed when the universe was barely 7% of its current age. The problem isn't that spiral galaxies exist. It's that making one requires time. Lots of it. In the standard picture of galaxy formation, structures grow through hierarchical assembly. Small clumps of dark matter collapse first, pulling in gas. Those clumps merge, forming larger structures. Those larger structures merge in turn. Eventually, after billions of years of collisions, accretion, and gravitational stirring, you might get something resembling an organized spiral. JWST skipped that entire process. Or compressed it into an impossibly brief window. The galaxy's mass, roughly 5 times that of the Milky Way, compounds the mystery. That much stellar mass requires converting enormous amounts of gas into stars, sustaining high star formation rates for extended periods. But extended is relative. At 1 billion years after the Big Bang, extended means hundreds of millions of years at most. That's not enough time under conventional models. Then there's Ulkananda, another spiral discovered by Indian astronomers, existing when the universe was 1.5 billion years old. It displays the same organized structure, the same symmetric arms, the same central concentration of stars. And it's forming stars at roughly 20 times the Milky Way's current rate, burning through its gas reservoir at a pace that should exhaust it within a few hundred million years. What's striking isn't just their existence, but their perfection. These aren't messy proto-galaxies showing hints of spiral structure. They're mature systems with well-defined arms, stable rotation, organized star formation patterns. They look like galaxies that have had time to settle, to smooth out irregularities, to establish equilibrium. But they haven't had that time. Unless something about the early universe made galaxy formation fundamentally more efficient. Unless the processes that take billions of years today could be compressed into hundreds of millions back then. One possibility involves gas accretion rates. In the current universe, galaxies acquire gas relatively slowly, through gentle infall along cosmic web filaments. But in the dense early universe, gas might have flooded into galaxies in violent torrents, cold streams falling directly into dark matter halos without the gradual heating that characterizes later epochs. Those cold streams would have been ideal for star formation. Gas at lower temperatures fragments more easily, collapsing into molecular clouds that birth stars with high efficiency. If early galaxies received gas this way, they could have sustained star formation rates far exceeding what their modern counterparts achieve. But that still doesn't explain the organized structure. Spiral arms aren't random. They're density waves, coherent patterns that persist even as individual stars orbit the galactic center. Creating them requires specific conditions: a rotating disk with the right mass distribution, enough time for gravitational instabilities to amplify into organized patterns, feedback mechanisms that prevent the disk from fragmenting completely. Getting all those conditions aligned in a chaotic young universe seems unlikely. Yet there they are, spiral galaxies with textbook morphology, existing when conventional wisdom says they shouldn't. The discoveries extend beyond spirals. Webb has also found barred spiral galaxies, systems with elongated stellar bars stretching through their centers, appearing as early as 2 billion years after the Big Bang. Cosmos 74706 displays a prominent bar, a linear concentration of stars and gas running across its nucleus. The Milky Way has a similar bar. But the Milky Way is 13.6 billion years old. Cosmos 74706 existed when the universe was less than 2 billion years old. Bars form through specific dynamical processes. They're not initial conditions but evolved features, arising when disk galaxies reach certain thresholds of mass and rotation. Simulations suggest bars typically form several billion years into a galaxy's life, after the disk has had time to stabilize and develop the right orbital resonances. Finding them this early suggests either galaxies evolved faster than simulations predict, or the early universe provided conditions that accelerated bar formation. J0107A takes it further. This monster galaxy, with a mass more than 10 times the Milky Way's and a star formation rate 300 times higher, displays what astronomers describe as a perfect barred spiral structure. One of the largest and most distinct bars observed from this cosmic epoch. The galaxy shouldn't just be big. It shouldn't be organized. Rapid star formation tends to create irregular morphologies. All that stellar feedback, supernovae exploding, massive stars ejecting material through powerful winds, should disrupt orderly structures. The fact that J0107A maintains such a clean spiral pattern while forming stars at such extreme rates defies intuition. It's like watching a city experience explosive growth while maintaining perfect urban planning. Possible in theory, but requiring coordination that seems unlikely without some organizing principle we're missing. What could that principle be? Dark matter provides the gravitational scaffolding for galaxy formation. Its distribution determines where gas accumulates, how fast structures grow, whether galaxies merge or evolve in isolation. If dark matter halos in the early universe had properties different from those in the current cosmos, that could explain accelerated structure formation. But changing dark matter behavior requires modifying fundamental physics. Not impossible, but a step most astronomers prefer to avoid unless absolutely necessary. A less radical explanation involves feedback mechanisms. In the current universe, star formation is self-limiting. Massive stars inject energy into their surroundings, heating gas, driving winds that expel material from galaxies. This negative feedback prevents galaxies from converting all their gas into stars too quickly. Maybe in the early universe, feedback was less effective. Dense environments might have allowed gas to cool faster, recovering from stellar heating on shorter timescales. If gas could collapse again soon after being disrupted, star formation could proceed more continuously, building stellar mass faster without destroying the organized structures forming simultaneously. Or maybe the initial conditions were just different. Maybe those tiny density fluctuations seeded by quantum processes in the first instance after the Big Bang weren't as uniform as we thought. Maybe there were occasional peaks, regions where density variations were strong enough to jumpstart structure formation earlier than average. That would create a universe with more diversity than standard models predict. Most regions following the expected timeline, but a few rare zones racing ahead, forming mature galaxies while their surroundings still hosted primitive structures. Webb's field of view is small. It samples tiny patches of sky. If organized spiral galaxies are rare but not impossible, Webb might be catching the exceptional cases, the statistical outliers that exist in small numbers but reveal what's possible under favorable conditions. That interpretation preserves the standard cosmological model while accommodating unexpected observations. It suggests we're not seeing the typical early universe, but the extreme tail of the distribution. Yet even that explanation faces challenges. The number of mature galaxies Webb finds keeps growing. Each new observation adds to the population. At some point, outliers become common enough that calling them outliers stops making sense. Which leaves us with a cosmology that works beautifully for most of cosmic history but struggles with the first billion years. A framework that successfully describes galaxy formation in the mature universe but can't account for what happened when everything was young, dense, and evolving faster than equations predict. And the mysteries don't stop with structure. Webb has also revealed unexpected chemical enrichment in these early galaxies. Elements heavier than hydrogen and helium, forged in stellar cores and dispersed by supernova explosions, appearing in concentrations that require multiple generations of stars. JWST 14-0, observed just 280 million years after the Big Bang, shows elevated nitrogen levels. Nitrogen production requires massive stars to form, devolve, explode, then a second generation of stars to incorporate that nitrogen and produce even more. That's a complex cycle that should take considerable time. Finding it complete this early means stellar evolution proceeded at an accelerated pace. Stars formed, lived their lives, died, enriched their surroundings, and seeded new stars, all within a few 100 million years. Or it means we don't understand stellar nucleosynthesis as well as we thought. Maybe certain conditions in the early universe allowed different nuclear reaction pathways, producing heavy elements faster than current models allow. Either way, the chemistry doesn't match the timeline. And when chemistry and timelines conflict, something in our understanding needs revision. Then there's the black hole problem. Webb's observations have revealed supermassive black holes existing far earlier than they should. Not just early, but massive. Black holes containing millions or even billions of solar masses appearing when the universe was less than 1 billion years old. Standard theory holds that black holes grow through accretion, pulling in surrounding matter over time. Massive stars die, collapse, form stellar mass black holes, then gradually accumulate mass. Or they grow through mergers, smaller black holes combining into larger ones. Both processes require time. Feed a black hole at the maximum theoretical rate, and it still takes hundreds of millions of years to reach supermassive status starting from stellar remnants. Yet Webb finds these behemoths already in place just a few 100 million years after the Big Bang. The timeline doesn't work. Unless black holes formed differently in the early universe. One possibility involves direct collapse. Instead of forming from dying stars, maybe primordial gas clouds collapse directly into black holes under specific conditions. Dense regions of pristine hydrogen, never contaminated by heavy elements, might have been able to collapse catastrophically, bypassing the stellar phase entirely. That would create intermediate mass black holes right from the start, giving them a head start on growth. But direct collapse requires very specific conditions. The gas must be hot enough to avoid fragmenting into stars, yet dense enough to overcome pressure and collapse gravitationally. Finding those conditions frequently enough to explain Webb's observation stretches plausibility. Another explanation involves primordial black holes, hypothetical objects formed in the extreme density fluctuations of the very early universe, possibly in the first fraction of a second after the Big Bang. If such objects existed and survived, they'd have billions of years to grow before the first galaxies formed. That extends the available timeline significantly. But primordial black holes remain speculative. No direct evidence confirms their existence. Using them to explain observations requires invoking something we haven't proven exists to solve a problem we didn't know we had until recently. What makes this especially puzzling is that these early black holes aren't hiding. They're actively feeding, pulling in gas and radiating energy as quasars, some of the brightest objects in the universe. That means they're not just massive, they're already dominating their host galaxies, influencing star formation, heating surrounding gas, shaping galactic evolution. The relationship between galaxies and their central black holes is supposed to develop gradually over cosmic time. Yet here it is, fully established when the universe was still in its infancy. And some of these objects are stranger still. Webb has identified galaxies that look completely ordinary in visible light but transform when observed in infrared. One example, nicknamed Virgil, appears as a normal star-forming galaxy in optical wavelengths. Switch to mid-infrared, and a hidden monster emerges. A dust-obscured supermassive black hole, actively accreting, hidden behind thick clouds of gas and dust that block visible light but glow in infrared. This raises an uncomfortable question. How many other black holes are we missing? How many galaxies harbor hidden central engines that only reveal themselves at specific wavelengths? If dust-obscured black holes are common in the early universe, our census of these objects is incomplete. We've been systematically missing a population that might be crucial for understanding cosmic evolution. These hidden black holes could explain part of the reionization mystery. The epoch of reionization, when neutral hydrogen filling the universe became ionized, requires a massive energy source. Stars provide some of that energy. But if there's a hidden population of actively feeding black holes, their contribution to reionization might be larger than previously estimated. Quasars blast out enormous amounts of ultraviolet radiation, exactly what's needed to ionize hydrogen. If we've been undercounting them, we've been underestimating their role in one of the universe's major transitions. Webb has also discovered objects that don't fit existing categories. Little red dots, small red sources appearing in large numbers around 600 million years after the Big Bang, then declining rapidly by 1.5 billion years. They're too red to be normal star-forming galaxies, too compact, too bright. Their spectra show unusual features that don't match standard galaxy classifications. Some researchers think they might be dust-obscured black holes. Others suggest they could be extremely dense star-forming regions. Or perhaps they're something entirely new, a class of object that only existed briefly in the early universe then disappeared as conditions changed. The problem is that every new category of object, every unexpected discovery, adds complexity to an already strained theoretical framework. Each mystery might have its own solution. Spiral galaxies form faster because of specific feedback mechanisms. Black holes grow through direct collapse. Little red dots represent a transitional phase. Chemical enrichment proceeds via alternative nucleosynthesis pathways. But at some point, invoking separate explanations for each anomaly stops being satisfying. The pattern suggests something more fundamental might be wrong. Consider the sheer abundance of massive galaxies. Webb keeps finding them, in numbers far exceeding predictions. Statistical models based on standard cosmology predict only a handful of ultramassive galaxies in the observable patches Webb surveys. Instead, there are dozens. That's not a minor discrepancy. That's an order of magnitude difference. You can't explain that away with measurement uncertainties or selection effects. The universe simply contained more massive galaxies at early times than our models allow. One response is to adjust the models. Maybe star formation efficiency was higher. Maybe feedback was weaker. Maybe initial density fluctuations had a different distribution. Each adjustment brings models closer to observations. But the adjustments are becoming substantial. We're not fine-tuning parameters anymore. We're reconsidering fundamental assumptions about how structure formation proceeds. Another response is to question whether we're interpreting the observations correctly. Maybe what looks like a massive galaxy is actually something else. Multiple smaller galaxies aligned along our line of sight, appearing as a single bright source. Or gravitational lensing amplifying distant objects, making them seem brighter and more massive than they are. Webb's resolution is excellent, but it's not perfect. Confusion is possible. Except that detailed analysis keeps confirming the initial interpretations. These are indeed individual massive galaxies, not chance alignments or lensing artifacts. The observations hold up under scrutiny. Then there's the question of whether standard cosmology itself needs revision. The Landis-EDM model, cold dark matter with a cosmological constant, explains the large-scale structure of the universe remarkably well. Observations of the cosmic microwave background, galaxy distributions, and the expansion rate all fit within this framework. But Landis-EDM was calibrated using the mature universe. Maybe it breaks down in extreme conditions, during the first billion years when densities were higher, processes faster, physics pushed to limits we don't normally encounter. That doesn't mean abandoning the model entirely. It means recognizing its boundaries, understanding where it applies and where it doesn't. What's becoming clear is that the early universe was a different beast. Not just younger, but qualitatively different in ways that matter. The rules we've learned from studying galaxies over the past 10 billion years might not apply to the first billion. Extrapolating backward assumes continuity, that the same physical processes operated the same way across all epochs. Webb is revealing that assumption might be too simple. The universe has evolved not just in structure but in behavior, in how efficiently it forms stars, grows black holes, assembles galaxies. Understanding cosmic dawn requires more than running our current models in reverse. It demands building new theoretical frameworks from the ground up. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will expand this investigation dramatically. Where Webb peers deeply at small patches of sky, Roman will survey vast areas with comparable sensitivity. Its wide field of view means finding not dozens but potentially thousands of these enigmatic early galaxies. Statistical samples that large transform the game entirely. Individual anomalies become population studies. Patterns emerge from noise. Questions shift from, is this real? To, what does the distribution tell us about underlying physics? Combining Roman surveys with Webb's detailed spectroscopy creates a powerful synergy. Roman identifies candidates across enormous sky areas. Webb follows up with deep observations, dissecting their chemistry, kinematics, stellar populations. Together they map cosmic dawn in unprecedented detail, revealing not just what existed but how structures evolved, how galaxies interacted, how the first billion years unfolded. Ground-based telescopes contribute as well. The extremely large telescope under construction in Chile will have a mirror 39 meters across, dwarfing anything currently operational. Its resolution and light-gathering power will complement Webb's infrared capabilities, providing optical and near-infrared observations that probe different physical processes. Multi-wavelength coverage matters because galaxies emit across the electromagnetic spectrum. Each wavelength reveals different components, different temperatures, different dynamics. Radio observations trace cold gas, the raw material for star formation. X-ray telescopes like Chandra detect hot gas in active black holes. Ultraviolet instruments probe young massive stars. Combining all these perspectives builds complete pictures, moving beyond single wavelength snapshots to integrated understanding. But instruments alone don't solve mysteries. They generate data. Making sense of that data requires theory, simulations, models that connect observations to physical processes. And that's where things get interesting. Traditional approaches to galaxy formation start with dark matter. Simulations track how dark matter clumps under gravity, forming halos that attract normal matter. Gas falls into these halos, cools, fragments, forms stars. Over time, small halos merge into larger ones, building galaxies hierarchically from the bottom up. This framework works remarkably well for the mature universe. Simulations reproduce observed galaxy populations, their sizes, masses, star formation rates. But when applied to cosmic dawn, the same models struggle. They produce too few massive galaxies too slowly. Adjusting parameters helps, but only to a point. Beyond a certain threshold, adjustments become arbitrary, losing predictive power. Alternative models explore different physics. Maybe gas cooling was more efficient in the early universe, allowing rapid star formation. Maybe feedback from supernovae and black holes operated differently when metallicities were low and gas densities high. Maybe dark matter itself behaves in ways not captured by standard cold dark matter assumptions. Some researchers propose warm dark matter, particles with slightly higher velocities that suppress small-scale structure formation. Others investigate self-interacting dark matter, where dark matter particles scatter off each other, altering halo profiles. These variations change how galaxies form, potentially explaining why early galaxies appear more massive and mature than standard models predict. Then there's the possibility that we're misinterpreting the observations themselves. Systematic errors in measuring distances, masses, or star formation rates could skew results. If redshifts are slightly off, galaxies appear closer and therefore less extreme. If dust corrections are wrong, masses get overestimated. Every measurement involves assumptions, and assumptions can be wrong. Except that cross-checks keep validating the data. Independent distance indicators agree. Spectroscopic conformations match photometric estimates. Multiple teams using different methods reach similar conclusions. The observations hold up. These galaxies really are as massive, as chemically enriched, as structurally complex as they appear. Which brings us back to fundamental questions. If standard models can't explain what we see, what does that mean? Are we missing key physics? Is our understanding of stellar evolution incomplete? Do we need to rethink how black holes grow, how galaxies merge, how cosmic structure assembles? Or is the problem deeper still? Landis EDM cosmology rests on general relativity, quantum field theory, and observational constraints from the cosmic microwave background. Those foundations are solid, tested extensively. But they describe the universe at large scales, averaged over vast volumes. Cosmic dawn represents extreme conditions, high densities, rapid evolution, physics pushed to limits. Extrapolating from current conditions to those extremes assumes continuity. Maybe that assumption fails. Consider initial conditions. The cosmic microwave background shows tiny fluctuations in density, seeds that grew into galaxies. Standard inflation models predict specific statistical properties for these fluctuations, and observations match beautifully. But inflation is still theoretical, and alternative models exist. If initial conditions differed even slightly from standard assumptions, structure formation would proceed differently. Another angle involves dark energy. We know it exists because the universe's expansion is accelerating, but we don't know what it is. The cosmological constant fits observations, but it's essentially a placeholder, a number inserted into equations. If dark energy evolved over time, varying in strength or properties, cosmic history would differ from standard predictions. Early dark energy models explore this possibility, suggesting that dark energy was stronger in the past, affecting how structure formed. These aren't fringe ideas. They're serious proposals being actively investigated. The point isn't that any particular alternative is correct, but that we're operating in a regime where fundamental assumptions deserve scrutiny. Webb isn't just collecting data. It's testing the limits of our cosmological framework. Every discovery raises new questions. Why do some galaxies contain supermassive black holes while others don't? What triggers star formation bursts? How do spiral structures form so quickly? Why are certain chemical elements overabundant? Each question connects to deeper physics, to processes we don't fully understand. The humbling part is recognizing how much we still don't know. A century ago, we didn't know galaxies existed beyond the Milky Way. 50 years ago, we didn't know about dark matter or dark energy. 20 years ago, we couldn't observe cosmic dawn directly. Each leap in capability reveals new complexity, new layers we hadn't imagined. Webb represents the latest leap, but it won't be the last. Future missions will go further, see clearer, probe deeper. Each generation of instruments refines our view, corrects misconceptions, opens new frontiers. The process never ends because the universe is vast and intricate beyond comprehension. What we're witnessing now is science in action, the messy iterative process of confronting theory with observation, adjusting when they conflict, pursuing new ideas when old ones fail. There's no grand revelation coming that suddenly makes everything clear. Understanding emerges gradually, piece by piece, through countless small advances. But those advances matter. They reshape how we see the universe, our place in it, the history that led to us. Cosmic dawn isn't just abstract astrophysics. It's the era when matter first organized into structures complex enough to eventually produce stars, planets, life. Understanding how that happened, what conditions enabled it, what physical laws governed it, connects directly to why we exist. The hidden structures Webb reveals in distant galaxies aren't just beautiful images. They're evidence of processes that sculpted the cosmos, that transformed primordial simplicity into layered complexity. Every spiral arm, every chemical signature, every massive black hole tells part of that story. We're learning to read it, slowly, imperfectly, but persistently. And perhaps the most profound lesson is this: the universe doesn't conform to our expectations. It operates according to physical laws we're still discovering, through mechanisms we're still piecing together. Every time we think we've figured it out, new observations challenge our understanding, forcing us to think harder, look closer, question deeper. That's not a failure of science. That's science working exactly as it should, revealing a universe far stranger and more magnificent than we ever imagined. It requires accepting uncertainty. Admitting when models break down, when predictions fail, when the data simply doesn't match what theories demanded. That acceptance isn't weakness. It's intellectual honesty, the foundation of genuine progress. Webb's revelations about the early universe force that honesty. These aren't minor discrepancies that disappear with better statistics. They're fundamental challenges to how we understand cosmic structure formation. Galaxies too massive, too organized, too chemically evolved for their age. Black holes appearing far earlier than growth mechanisms allow. Spiral structures developing on timescales shorter than gravitational processes should permit. Each observation stands alone as a puzzle. Together they form a pattern suggesting our framework for the first billion years needs serious reconsideration. Not abandonment, but evolution. The Landis EDM model successfully describes the large-scale universe. It matches cosmic microwave background fluctuations precisely. It predicts galaxy clustering statistics accurately. But extending it backward to cosmic dawn, applying it to conditions far more extreme than those it was calibrated against, produces predictions that don't match reality. That mismatch reveals boundaries. Every scientific model has limits, domains where it applies and domains where it breaks down. Classical mechanics works beautifully at human scales but fails for objects moving near light speed or existing at quantum scales. General relativity describes gravity across cosmic distances but clashes with quantum mechanics at the smallest scales. Models aren't truth, they're tools. Useful within their valid ranges, misleading beyond them. Perhaps standard cosmology's valid range doesn't extend to the universe's first billion years. Perhaps that epoch operated under different effective rules, not because physical laws changed but because extreme conditions produce behaviors our models don't capture. High gas densities might have made star formation more efficient. Lack of heavy elements might have altered cooling mechanisms. Stronger tidal forces in the compact early universe might have triggered different merger dynamics. Understanding those differences requires moving beyond parameter adjustments. It demands investigating new physics, exploring mechanisms not relevant in the mature cosmos. Maybe massive stars formed preferentially in pristine gas, creating stellar populations unlike anything seen today. Maybe direct collapse black holes seeded supermassive growth in ways stellar remnants couldn't. Maybe cold gas streams fed star formation continuously rather than episodically. These aren't wild speculations. They're testable hypotheses grounded in known physics applied to unfamiliar conditions. The challenge is connecting them to observations, building models that reproduce what Webb sees without contradicting what else we know about the universe. That work is ongoing. Theorists worldwide are revising simulations, testing new assumptions, exploring alternative scenarios. Not everyone agrees on the solutions. That's healthy. Science advances through competing ideas tested against evidence, not consensus enforced prematurely. What everyone does agree on is that something needs to change. The observations are too robust, too consistent across multiple independent measurements to dismiss. These galaxies exist. Their properties are real. Any viable cosmological framework must account for them. Future observations will constrain possibilities. Raman-wide surveys will reveal whether massive early galaxies are rare outliers or common populations. Follow-up spectroscopy will measure their chemical compositions precisely, determining whether exotic nucleosynthesis pathways are necessary or standard processes suffice given higher efficiencies. Gravitational lensing studies will test whether some apparent giants are actually magnified smaller galaxies. Each new constraint eliminates possibilities, narrowing the solution space. Eventually patterns will emerge. Certain modifications will consistently improve agreement between models and data. Others will prove insufficient despite initial promise. The path forward isn't obvious now, but it will become clearer as evidence accumulates. That's the power of empirical science. Nature doesn't care about theoretical preferences. It simply is. Our job is figuring out what is, adjusting our understanding to match reality rather than insisting reality conform to our expectations. Webb has shown us reality deviates from expectations dramatically during cosmic dawn. Accepting that deviation opens doors. Maybe the early universe was more violent than we thought, with frequent galaxy collisions driving rapid mass assembly. Maybe feedback mechanisms were weaker, allowing gas to remain available for star formation longer. Maybe dark matter halos had different concentration profiles, affecting how baryonic matter accumulated. Each possibility leads somewhere different, predicts different future observations. Testing them systematically separates viable explanations from dead ends. It's painstaking work, requiring careful analysis of massive datasets, sophisticated modeling, rigorous statistical methods. Not glamorous, but essential. And occasionally, brilliantly illuminating. Because hidden in those datasets are answers to profound questions. When did the first stars ignite? How did supermassive black holes form? What drove reionization? How did galaxies acquire their structures? These aren't academic puzzles. They're chapters in the universe's history, the story of how simple beginnings evolved into stunning complexity. We're reading that story backward, looking at ancient light carrying information across billions of years. Every photon Webb collects traveled through expanding space, redshifted by cosmic expansion, preserved against all odds to reach our instruments. The fact that we can decode those photons, extract temperatures and compositions and velocities from spectral lines, reconstruct three-dimensional structures from two-dimensional images, demonstrates how far scientific capability has advanced. But it also demonstrates how far we have yet to go. The questions we can answer now would have seemed miraculous to astronomers a century ago. The questions we can't answer yet will seem mundane to astronomers a century hence. Progress continues because each answer reveals new questions, deeper mysteries, richer complexity. Webb isn't the end point. It's a milestone in ongoing exploration. Decades from now, new telescopes will observe wavelengths Webb can't access, achieve resolutions Webb can't match, study objects Webb can't detect. They'll build on Webb's discoveries the same way Webb builds on Hubble's, Spitzer's, every previous mission that expanded humanity's cosmic vision. That continuity matters. Science isn't individuals having brilliant insights in isolation. It's communities building knowledge incrementally, each generation standing on previous foundations, reaching slightly higher, seeing slightly farther. Webb's team includes thousands of people across dozens of countries, engineers and scientists and technicians whose combined expertise made this instrument possible. Their work enables discoveries that challenge comfortable assumptions. That's exactly what great instruments should do. Not confirm what we already believe but force us to confront what we don't understand, revealing the boundaries of knowledge so we can push past them. The hidden structures Webb reveals in distant galaxies represent those boundaries made visible. Each massive early galaxy marks a gap between theory and observation. Each dust-obscured black hole highlights incompleteness in our census. Each chemical abundance anomaly points toward stellar physics we haven't fully grasped. Closing those gaps won't happen overnight. It requires sustained effort across multiple disciplines, combining observations with theory, simulations with data analysis. Some mysteries will yield quickly once the right insight clicks. Others will resist for years, requiring entirely new approaches or technologies not yet invented. But they will yield eventually. History proves it. Every mystery that seemed intractable ultimately surrendered to persistent investigation. Continental drift. Stellar energy sources. Cosmic expansion. Quantum mechanics. Each represented a fundamental shift in understanding, achieved not through single revelations but accumulated evidence forcing unavoidable conclusions. We're in that accumulation phase now regarding cosmic dawn. Webb provides evidence. Theorists struggle to accommodate it. Tensions mount between observations and models. Something will give. Either observations will reveal subtleties that resolve apparent conflicts, or models will evolve to match what nature actually does rather than what equations predicted. My bet is on the latter. The observations are too solid, too multifaceted, too independently confirmed. These galaxies really are more massive, more structured, more chemically evolved than standard models allow. Explaining them requires revising our understanding of early star formation, black hole growth, galaxy assembly. That revision is already underway. Papers proposing new mechanisms appear regularly. Simulations test alternative physics. Observers design follow-up programs targeting specific predictions. The scientific process works, messy and contentious and slow, but ultimately effective. Because at its core, science is about getting closer to truth. Not possessing absolute truth, that's beyond reach. But approaching it asymptotically, reducing uncertainty, replacing speculation with knowledge, transforming mysteries into understanding. Webb accelerates that transformation by providing data previous instruments couldn't access. Infrared vision penetrating dust. Spectral resolution revealing chemistry. Sensitivity detecting objects billions of light-years distant. Every technical capability translates to scientific opportunity, chances to test ideas, probe phenomena, answer questions. And ask better ones. Because the most important questions emerge from answers. You can't ask, why do spiral galaxies form so early? Until you know they do. You can't investigate dust-obscured black hole populations until you detect individual examples. You can't study chemical enrichment timescales until you measure abundances at different epochs. Webb enables those measurements. What we do with them determines how much we learn. Simply cataloging discoveries provides value, building databases for future researchers. But real understanding comes from synthesis, from connecting observations to physical processes, from building frameworks that explain not just what we see but why it had to be that way. That deeper understanding awaits. We're still in the surprise phase, where each new discovery challenges expectations. Eventually we'll transition to the comprehension phase, where patterns clarify and explanations cohere. Not yet, though. We're still figuring out what questions to ask, which anomalies matter most, where to focus limited observing time. That's the exciting part. The frontier is wide open. Every observation could reveal something unprecedented. Every dataset contains potential breakthroughs. We're exploring unknown territory with instruments powerful enough to actually map it, not just glimpse it from afar. The hidden structures in distant galaxies aren't just beautiful or interesting. They're evidence of cosmic processes we're only beginning to understand, mechanisms that shaped the universe during its most formative period. Understanding those mechanisms matters because they set initial conditions for everything that followed. The galaxies we see around us today, including our own Milky Way, descended from structures that formed during cosmic dawn. Their properties, their distributions, their evolutionary paths all trace back to those first billion years when physics operated at extremes we can barely simulate. Getting that era right is essential for understanding cosmic history comprehensively. Webb gives us tools for getting it right. Not instantly, not easily, but eventually through careful systematic investigation. The data exists. The instruments work. The community is engaged. Progress is inevitable, even if the path remains unclear. What that path reveals will reshape cosmology. Maybe subtly, through refined parameters and improved models. Maybe dramatically, through fundamental reconceptualizations of how structure forms. Either way, our picture of the universe will change, become more accurate, align better with reality. That's the goal. Not defending theories or protecting reputations, but understanding how the universe actually works. Webb's observations of hidden structures in distant galaxies serve that goal by revealing where our understanding falls short, where reality exceeds expectations, where mysteries remain. Those mysteries won't stay mysteries forever. Someone will solve them, connecting observations to physics in ways that make everything click. Maybe that someone is working on it right now, analyzing Webb data, running simulations, having the insight that unlocks the puzzle. Or maybe it'll take decades, require new instruments, new theoretical frameworks, perspectives we haven't developed yet. Either way, the answer exists out there in the data, waiting to be found. Because the universe doesn't hide its secrets maliciously. It simply operates according to physical laws. Our job is learning those laws well enough to predict what they produce, then testing those predictions against what actually exists. When predictions fail, we learn. When they succeed, we confirm. Both outcomes advance understanding. Right now we're in the learning phase. Webb's early galaxies don't match predictions. That failure teaches us something fundamental about cosmic dawn, something models missed. Figuring out what we missed is the challenge. Meeting that challenge will reveal truths about the universe's first billion years, about how matter organized into structures, about the physical processes that transformed primordial simplicity into cosmic complexity. And in that transformation lies our own origin story. Because those early galaxies eventually evolved into later ones, which hosted stars that created heavy elements, which enabled planets, which provided environments where life could emerge. The chain extends from cosmic dawn to human consciousness, every link essential, every step governed by physics we're still decoding. Webb helps us decode it by showing what the early universe actually looked like, not what we thought it should look like. That's the value of observation over theory, of evidence over assumption. Nature reveals truth. Our task is paying attention, interpreting correctly, adjusting understanding to match reality. The hidden structures in distant galaxies represent reality exceeding imagination. We imagined a simple early universe, gradually building complexity. Reality delivered a dynamic cosmos, rapidly assembling massive structures, organizing matter efficiently, producing diversity we didn't anticipate. That's not failure on our part. That's the universe being more interesting than our models predicted. And more interesting means more to discover, more to understand, more opportunities for insights that reshape how we see everything. The work continues, driven by curiosity about our cosmic origins, about the physical laws governing existence, about the magnificent complexity arising from simple beginnings. Webb opened a window on that complexity. What we see through it challenges comfortable assumptions and demands better explanations. That's exactly what great science does. It forces us beyond what we think we know into territory where genuine understanding requires genuine effort, where easy answers don't exist, where reality insists on its own terms. Those terms are being negotiated now through observations, theories, debates, and discoveries. The outcome isn't certain, but the direction is clear. We're learning what the early universe was really like, adjusting our cosmological framework to accommodate that reality, building understanding that will stand as foundation for future generations who'll push even further into cosmic history. That's the legacy Webb creates. Not final answers, but better questions. Not complete understanding, but deeper insight. Not the end of cosmic exploration, but an essential chapter in humanity's ongoing effort to comprehend the universe that created us.